Hello students, welcome back. So up to this point, we have studied about what is electric current, what are the factors affecting electric current. We also study about the resistance, the factors affecting resistance which are intrinsic to conductor. We also studied about the power sources available with us, that is cell. We also studied about internal resistance, the combinations of cells both series and parallel, and in similar context we studied about resistance, series and parallel combination of resistors. Now we will use all of these concepts to shift our attention in solving the complex circuits available with us. With the help of laws given by Kirchoff and famous circuits, we will be able to solve the complex circuits. So let's start.
We will now try to focus our attention on the next part of the current electricity chapter. In the next part, we will be studying about the Kirchoff's law, that is, how to deal with the circuits which are complex in nature, that is, they are neither series nor parallel in a proper sense. Then we will study about the most famous circuit in current electricity, that is the Wheatstone bridge and its applications. So let's move on to the Kirchoff's law. So the first Kirchoff's law, that is the Junction Law, states the algebraic sum of electric currents at a junction in any electrical network is always 0. To better understand this, let's have a proper diagram. So I have this junction denoted by O, and I have incoming currents, that is I4 and I1. So I1 and I4 are coming into the junction, or let's say towards O. I2, I3 and I5, they're going out of O, that is, they're going away from the junction O. So according to the first law of Kirchoff, that is the junction law, the sum of these currents need to be 0 with due consideration of their sign, that is, they're going in or they're going out. So according to the sign convention, we have to take into consideration that the incoming currents to be positive, the outgoing currents to be negative. Now, what's the logic behind this law? The logic behind this law is, at the junction there is no storage device for the charge, or there is no sink such that there is a loss of charge. Hence, for the conservation of charge, the incoming currents has to be equal to the outgoing currents. So if we do take the signs of incoming and outgoing currents, we will get this expression, that is the junction law. So moving on to the second part of Kirchoff's law, that is the loop law. So the loop law, for the loop law, the statement goes like this: the algebraic sum of all the potential drop and EMFs along any closed path in an electrical network is always 0. So let us have a diagram corresponding to it with proper markations. So the current goes like this. So this is one loop. Correspondingly, the equation goes like this. There is another loop. Correspondingly, the equation from loop law goes like this. Now, the expression says, again, I would like to repeat it, the algebraic sum of all the potential drop and EMFs along any closed path in an electrical network is always 0. Now, why is that the case? That is, if I move from point C to B to A and back to C, or any other way, that is, if I need to have a closed path. So there are many possibilities of a closed path. Starting from point C, I can come back to C via A or via D. Even I can start from B and do the same. For A, I can do the same. So there are various alternatives possible. But for each closed path, the potential drop and the EMFs has to be 0. The sum of them, they have to be 0. Why is that the case? The reason is the conservation of energy. If you move in a closed loop, in a conservative field, the work done is 0. That's a property of conservative field. Now, the field which deals, or let's say when we move from point C to A, then back to C, we are moving in an electric field. Electric field is conservative in nature. So work done in moving from any point and coming back to the same point in an electric field is 0. Hence, loop law holds true. So if you have a look at this expression, that is for the loop A, B, C, A, we have taken into consideration that we are moving from A to B. So the work done in moving the charge from A to B is obviously negative, because we are trying to move from positive terminal to the negative terminal. So the work done by me in carrying a positive charge across this will be minus E1. Then I'm going against the current, that is, I'm going against the current of I1. So the work done by me will be I1R1. Similarly, for this end of the trip, it will be I1 plus I2 into R2. So the sum of these three will be 0 according to loop law, or let's say the other version of conservation of energy. Same goes for loop ACDA. In ACDA, I'm moving like this from here to here. So the current is I1 plus I2. So I1 plus I2 into R2 with a minus sign. Why? Because I'm moving with the current. So work done will be negative, because I will try to restrict it. Then we're moving in long I2, that is, for I2 I'm moving from C to D through the resistance R3, current of I2. So it will be minus I2 R3. Then I'm moving a charge from the negative terminal, let's say a positive charge, from negative terminal to a positive terminal. So I'm doing a positive work, which is equal to plus E2. So this gives me two sets of equation. The junction rule gives me another set of equation. So with the use of loop law and junction law, I can solve any circuit in this world. It's just a matter of me solving down equations, whether I need to solve 3 equations, 10 equations, or 100 equations, depending upon the complexity of the circuit. So now we'll move on to one of the most famous circuit in current electricity, that is the Wheatstone bridge. The setup kind of look like this. So here I have a setup, that is 4 resistors are connected like this. AB has a resistor of P, BC has a resistor of Q, CD has a resistor of S, and AD has a resistor of R. And connecting the points B and D, I have a galvanometer, and it's connected to a cell. So the current flows like this. It gets distributed according to the junction law, that is, let's say this is I1, so it definitely will be I minus I1. Again, the current reaches this point, that is point D, so again it splits up. So let's call this current to be Ig, so this one will be I plus Ig minus I1. As stated, it's I minus I1 plus Ig, and again applying the junction rule, we'll get this. The same current which goes out, it's the same current which comes in. Now this is the typical setup of Wheatstone bridge. But what's the beauty of it? In the next slide, so this is where we can apply the loop law. This is also where we can apply the loop law. So we'll observe through the equations of loop law what is the beauty of Wheatstone bridge in the next slide. So we'll apply the Kirchoff's loop law over here. So for the loop ABDA, we get this equation. For loop BCDB, we get this equation. Now if you put the current through the galvanometer to be 0, that is Ig to be 0, we get this beautiful expression. P by Q is equal to R by S. That's the relationship which we get while solving the Kirchoff's law. And applying it in Wheatstone bridge with the condition that current through the galvanometer is 0. Now, we move on to meter bridge. Meter bridge as in one of the applications of Wheatstone bridge. So this is how the meter bridge looks like. So this over here is a wire of, let's say from point A to point B is a wire of length 1 meter. That's why the name meter bridge. Now, the setup goes like this. It's being connected to a cell with a switch, and here I have a known resistor of known resistance. So this is a resistor of known resistance, and I'm connecting it with an unknown resistor. That is, I don't have any information about this resistor. So my intention is to find out the resistance of this X, that is this resistor. So From this point, I have a galvanometer which is free to move through a jockey. That is, I can connect the other end of the jockey along this line, this metal wire, which is a conductor. So the guiding principle is the same as the Wheatstone bridge. If the current in, let's say inside the galvanometer is zero, so there is no deflection in galvanometer, we'll get a unique condition, that is P by Q is equal to R by S. That is the ratio of these two resistors, that is this metal wire up to this point has a certain resistance. This is a known resistance. So the ratio of these two will be equal to the ratio of these two, the resistance of these two resistors. From that, we definitely know that this wire is of length 1 meter. We can also measure the length of AG, and the leftover will be 1 minus this length. So we can definitely calculate, as I said, it's L centimeter, so it will be 100 minus L centimeter. So again, same thing written, when the galvanometer current is made zero by adjusting the jockey position on the meter bridge wire for the given values of known and unknown resistance, we get this equation, that is R by X is equal to RAG by RJB, which implies R by X, again, if you consider this by this equals to this by this, it's one and the same thing if I consider this by this to be equal to this by this. So I have R by X is equal to AJ divided by JB, which gives me this expression. So this is the known resistance. I can measure this length. I definitely know what is this. I can find out the value of X. So this is one of the beautiful application of Wheatstone bridge. So therefore, the unknown resistance comes out to be this. So with the use of meter bridge, you can find out the unknown resistance quickly. You just need to measure the length and set the jockey to zero when moving it along the wire. Now comes another device, that is potentiometer. The potentiometer is sort of a meter bridge but with a large length, that is it's close to 4 meters or even 10 meters in good cases. So again, the setup goes like this, that I have a cell, an ammeter to record the current, this is a rheostat such that I can set the value of the resistance, and I have here the voltmeter. So we can definitely make out that the voltmeter, the reading of the voltmeter will be proportional to the length of the wire, right? Because V is equal to Ki being the resistance along between these 2 points. So V is definitely proportional to the current flowing in the wire. What's the application of potentiometer? The application of potentiometer is simply to find out the unknown value of the EMF. We want to find out the EMF of a cell, so we can use potentiometer for that. So here's a typical setup of how we come up with the value of EMF for an unknown cell. So I have connected a cell to this point, and the other end is connected to the galvanometer, through which there is a jockey which can slide on the wire like this. Now the guiding principle is to set Ig to be 0, that is the reading for galvanometer has to be 0. So that implies that the current flowing through this, that is resistance of the position of jockey, that is this, let's say L2 is the equilibrium length, then L2 times the current flowing in the circuit has to be equal to the EMF of the battery. So through this we can find out that E1 is equal to VA J1 is equal to I rho L1 by A, this being the resistance, this being the current. Similarly, I can find out that E2 is equal to VAJ2 equals to L rho L2 divided by A. So this is the guiding principle, same as that of Wheatstone bridge and the meter bridge. Now this is another way of looking at it, is the proper application of Kirchoff's junction rule and Kirchoff's loop rule. So this was all about the potentiometer. Then finally we get the answer to be E1 by E2 is equal to L1 by L2. We can compare the EMFs and also find out the unknown EMF through potentiometer. So now we'll try out an example corresponding to potentiometer. So the question states, the length of a potentiometer wire is L. A cell of EMF E is balanced at a length of L by 3 from positive end of the wire. If the length of the wire is decreased by L by 2, at what distance will the same cell give a balance point? So I have an EMF of E which gave me a balance point, right? Now let's say the balance point was L by 3, it's given to be L by 3 and the length was L. Now for the same cell, I need to find the balance point, right? So let's call this as L dash and the new length is 3L by 2. Definitely know that we can write this as E divided by L into L by 3 equals to E divided by the new length is now 3L by 2 multiplied by L dash. With this, we found out that L dash is equal to L by 2. So this is my new balance point.
So we just concluded the two laws given by Kirchoff, which actually helps us in solving the complex circuit in current electricity. We also studied about one of the most famous circuit in current electricity, that is the Wheatstone bridge, and its practical applications being meter bridge and potentiometer. So in the next part, we will study about why does a circuit heats up after a few minutes. So stay tuned for my next part.